Good morning to everyone. This is the 2019 DDAY. We have today the presentation of the candidates to the final examination. The candidates to the final examination are Guido Borghi, Giuseppe Fiameni, Luca Di Cecilia, Paolo La Torraca, Luca Magnotta. They have been evaluated to external reviewers. The evaluations say that their theses are very good, so they will be able to have the examination on March 6. You will have the official communication by the office just on Monday. And then we have the students of the cycle 32, that is the student that are in the third year of the PhD. And these students are many: Davide Abati, Giovanni Abruzzese, Federico Bolelli, Elena Cipressi, Marcella Cornia, Lucio Fanton, Luca Gagliardelli, Fabio Giovanardi, Andrea Palazzi, Dario Stabili. 3 of the PhD students of this cycle are outside for research, so their presentation will be shown at the end because we have the registration of their presentation. And then we will have the poster research activity of the PhD student of the cycle 33. And for these students, we have the panels here. They have to put the poster on the panels, and after they will have a speech of 3 minutes showing and explaining what is in their poster. And the students are Bergamini Luca, Bombarda Davide, Fabri Matteo, Morone Giovanni, Paganelli Matteo, Parmigiani Nicolò, Salierno Giulio, Zagni Nicolò. So we can begin the session. The students candidate for the final exam has 20 minutes, preferably 17 minutes, in order to have some space for question by the college committee. So please, the first candidate is Guido Borghi. You can.
Okay. Hello everyone. Okay, so hello everyone, I'm Guido Borghi. The title of my work is Depth-Based Personalities for Driver Monitoring and Human-Computer Interaction. My supervisor is Professor Rita Cucchiara, and my co-supervisor is Roberto Vezzani. My work has been based on 2 research topics. The first one is driver monitoring. Driver distraction is one of the most important causes in road crashes. So this is why in ImageLab we are studying a new driver monitoring system. There are 3 types of distraction, usually in literature, but we focus only on the first 2. The manual distraction, that is when the driver's hands are not on the steering wheel, and the visual distraction when the driver is not looking at the road. The second research topic is human-computer interaction. That is the discipline that study models and techniques for the interaction. Here you can see a brief historical evolution about interfaces. We focus in particular on natural user interfaces in which the interaction is not carried through physical devices, but the user can interact with the computer or with the system in general through gesture, body, and voice. Natural user interfaces are so extremely user-friendly and intuitive to use. To tackle these research topics, we propose to use computer vision algorithms and artificial intelligence. We identify some requirements. The first is light invariance, since vision-based systems have to be reliable, even in presence of dramatic light changes. And so we propose to use depth maps that are acquired with infrared sensors, in which each pixel contains the value of the distance between the sensor and an object in the acquired scene. The second requirement is non-invasiveness, since driver's movement and gaze must not be impeded during the drive activity. And so we propose to use new sensors that are cheap, accurate, and also have a small factor 4. An example is the Intel RealSense family, or the PicoFlex family. The final requirement is, the last requirement is real-time performance, since monitoring and interaction system have to be quickly detect anomalies and provide quick feedback. And so we adopt a specific design strategy based on shallow, deep neural network, and also, of course, we use graphic processing units. So given these two research topics, I'm going to show you the following task. The first is face translation, then head pose estimation, facial landmark localization, head detection, all applied in the automotive context. We point out that deep learning-based techniques require a huge amount of annotated data, and therefore we collect a new depth-based dataset. And also, thanks to the Facebook partnership, in ImageLab we have a very powerful GPU-based server. Let's start to see the collected dataset. The first one is Pandora, that has been created for the head pose and shoulder estimation task. And this is the first dataset that contains both head and shoulder angles, expressed as yaw, pitch, and roll. And the second dataset is Motormark, that has been collected for the facial landmark localization task in the automotive context. Both datasets are acquired with the Microsoft Kinect One, a depth sensor, and so they consist in both RGB and depth frames. Other datasets are terms collected for driver's hand detection and tracking, and it has been collected in a real car, as you can see in the image. And the last one, and the oldest one, is Kinteract. The dataset that this dataset has been collected for the human-computer interaction through body gesture. So let's move to the first task, face translation. The main question is it possible to generate gray level face images from the corresponding depth ones? The answer is yes, but the main idea is to add knowledge, the generated faces at training and testing time to improve the performance of the whole system. So we propose two versions of a new neural network that we call face from depth. The first version is based on a traditional convolutional neural network, a CNN, composed by a convolutional and max pooling layer, as you can see. We use a weighted loss. In particular, we use a bivariate Gaussian prior mask to highlight the central area in which we suppose that there is the face of the user. The second version is based on the conditional generative adversarial network paradigm. It's a very recent paradigm in our field. This is a sort of min-max game in which there are two networks, a generator and discriminator. The generator tries to generate realistic images, and the discriminator tries to understand which image is fake or is real. So in this game, we have two loss functions. The first one is the mean square error loss, and it is used to trying to preserve the general appearance of the face. The second loss, the most important loss, is the adversarial loss, and that try to preserve the realism of the image. Here you can see some visual comparison between the two versions of face from depth. computed on Pandora and BWI dataset. That is a publicly released dataset, very important in the head pose estimation task. And also the numerical result that you can see at the bottom confirm the better accuracy and realism of the second version of the network. Second task is head and shoulder pose estimation. That is the ability to infer the orientation of the person's head or shoulders relative to the view of a camera. We propose a complete pipeline that we call Poseidon. As you can see, there is an acquisition module. We use the Microsoft Kinect sensor to acquire only depth frame. Then we have the head localization module, in which we have a convolution neural network, of course, and this network outputs the X and Y coordinates of the head center. Thanks to these coordinates, we can crop the head, including only a minor part of the background, as you can see in the image at the bottom. Then we have the domain translation module that is based on the face from depth network that I showed you before. And then we have the core of the Poseidon pipeline, in which we have three networks. The first one receives as input depth images. The second one, the generated face of face from depth. And the last one receives the motion images that are optical flow images on computer on depth. We apply a double-step training procedure. In the first step, each individual network is trained separately. And then the last fully connected layer is removed, and then all the networks are merged and trained together with a normal L2 loss function. The output of the system is represented by 6 angles, 3 angles yaw picture roll for the head, and 3 angles yaw picture roll for the shoulder. Here you can see video showing Poseidon running in a real car. We acquired these images, placing a Kinect inside the real car. And you can see also numerical results, in particular on your left. There is the accuracy compute on the BWI dataset. You can note that Poseidon overcomes all the competitors present in the literature, also using different evaluation procedures. And on the right, you can see the accuracy for head and shoulder pose estimation. That is very good, compute on Pandora dataset. Next task is face verification. That is the comparison of 2 faces in order to determine whether they belong to the same person or not. It is a one-to-one comparison that is different from the face identification that is a one-to-many comparison. The idea is to exploit privilege information, so additional or privilege information knowledge is available only during the training phase. But it is able to improve the performance of the whole system during the testing phase. We propose a system that we call JANOSNet. It is based on Siamese networks. Here you can see the architecture of the Siamese network that we use, that is a shallow deep neural network. During the training phase, as said, we have 3 networks. The first one, Siamese network, receives as input depth maps. The last one, the green one, receives as input RGB images. And the middle one, that is called hybrid Siamese network, receive as input depth maps, but receive also the loss computed on the network that use RGB as input. So the final loss is a combination of all the loss that you can see, the final loss of each network and this hybrid loss. During the test phase, so we have only the first 2 networks. So we use only depth maps during the testing phase, and we combine the score of these 2 networks to obtain the final result. We test JANOSNet on the face verification task, of course. We know that JANOSNet architecture outperform the single Siamese model, so the hybrid network, the RGB and depth network, but also is in line with, its accuracy is comparable to well-known deep approaches like the FaceNet that is a very, very deep neural network based on a huge RGB dataset that we don't have in the depth domain. So this is the main problem. We test also JanusNet in the face identification tasks. So to deal with the one-to-many comparison, JanusNet is used to obtain a similarity score between every possible pair of images contained in the dataset that we use. And finally, we combine the result with using these three functions that you see. And the last table at the bottom, you see that JanusNet largely overcomes the competitor. Next task is facial landmark localization. That is the detection of the position of salient points of the human face. So in our case, the facial landmarks are eyes pupils, mouth corners, and the nose tip. We propose the following pipeline. In the first module, we have the acquisition and the pre-processing, so the normalization of depth maps. In the second step, we use a very shallow model of deep network to obtain a real-time performance. We use only 5 convolutional layers, very small, and 3 max pooling and fully connected layers. And then we use an LHU loss. The output is represented by 10 coordinates, X and Y coordinates for each of the 5 facial landmark points that we want to obtain in the output. Here you can see an example of the Motormark dataset. So with all facial landmark estimated on depth and RGB images. You can see that in the table on the left, your left, there are results obtained on Eurecom Kinect Face dataset, and our results are in line with the state of the art. And then you can see also that we conduct several experiments on the Motormark dataset, obtaining a very good accuracy. The last task is head or face detection. That is the ability to detect and localize one or more heads or face in image or videos. This is a traditional task of the computer vision, but only few work present in the literature tackle this task on different type of images, like depth maps or thermal camera and so on. We propose the following method. We use as input fully resolution depth maps obtained from, as usual, the Microsoft Kinect 1. The output is represented by a probability map in which the peak of this probability function represents the head center. And for the network architecture, we take inspiration from a very well-known work present in the literature that's called convolutional pose machines. But we modify the original architecture and reduce the number of the final parameters to deal with real-time performance and the lack of training data in the depth domain. And the final accuracy is evaluated through the intersection over unit metric, in which we use a threshold set to 0.5. Here you can see a video running the pipeline. You can see the probability map function, peak, and also the depth map with the bounding box of the head. On the table on the top one, you can see that we achieve state-of-art results. We overcome all the competitors present in the literature, running only on depth images. And you can see also the rate of true head detection and speed performance over the change of input shape, since we use a fully convolutional network, so we were able to modify the shape of the input. The final part of my presentation is dedicated to Mercury, that is a framework for driver monitoring and human-car interaction. Here you can see the graphical user interface that we developed at ImageLab. In the first column, we have the acquisition part obtained with Microsoft Kinect. We use both RGB and depth frames. The second column is the head detection, is dedicated to head detection. We compute head detection both on RGB and depth images. We use Violen-Jones algorithm on the RGB and our methods on depth. Then we have the third column, this is in which we have the head pose estimation task represented by 3 color columns. and a 3D cube. And then we compute the facial landmarks only on RGB images. We are working to apply the facial landmark on that maps. And with these points, we crop the eyes of the driver to compute the values contained in the last column that is dedicated to driver's attention. We compute, for example, the pair close measure, that is a measure about the driver drowsiness level. And we, thanks to the head pose information, we compute the coarse gaze estimation, so we are able to understand where the driver is looking. And finally, we develop a system for a smart drive-car interaction to understand what object the driver is looking inside the car. So I spent also 4 months in Stanford University last year, and I developed a system for the human-robot interaction. I use as a robot the Jack robot that you can see on the top right border of the slide, corner of the slide. And I developed a system to understand the presence of interaction between the robot and a user. So the question is the robot facing the user? To develop the system, I use the Poseidon system. So I use depth maps acquired with a Microsoft Kinect placed on the top of the head of this robot. And then I implement a well-known work present in the literature that's called eye tracking for everyone to conduct a fine gaze estimation. So you can see the fine gaze estimation in the square, black square with the notation up, down, right, and left. And it is running only when the subject is in a frontal position. So thank you for your attention. Here you can see a list of my publication published during my PhD period. And also we are patenting a method, and I cite also my the thesis that I co-supervise that helped me during my PhD. Thank you.
Thank you, Guido. Questions from the Commission? Domenico?
My question is related to your proposal to add knowledge to the process, in particular for face recognition.
Okay.
My question is, this knowledge is also semantic knowledge, for example, deriving from ontologies or knowledge bases?
No, for now, the additional information is based only on images. We want to merge different image modality, so we exclude for this moment the information that you refer to, but we are planning to include in the system this information.
Thank you.
Thank you. So, Giuseppe, please. I ask for a swap because we have the tutor of Luca Di Cecilia who has examination. So, please, Luca. And Luca Di Cecilia, the title of his thesis is Novel Optoelectronic Methods and Techniques for the Early Detection of Ocular Diseases. And here on the table, you find the other main organization person of the doctorate. We have the Vice Dean, Luca Selmi. Luca? The coordinator of the Industrial Application Curriculum, Laura Giarrè. Domenico Beneventano for Computer Science. You have Giorgio Vitetta, who sits there for Electronics and Telecommunication. And we have Luca Vincetti, Luca, who is the referent person, the president of the Didactical Commission of the Doctorate. So for the young PhD student, you have the reference to other persons who are involved in the organization of our PhD. Luca, please.
Okay, thank you. My name is Luca Di Cecilia, and today I'm here to describe my work, that is entitled Novel Optoelectronic Methods and Techniques for the Early Detection of Ocular Diseases, that I did under the supervision of Professor Rovati. So first, I want to make a short introduction just to give you an overview of the reasons that guided our research. So, well, we all love our families, whether we have children, nephews, or grandchildren. The most important thing is the way we interact with them and to see them grow and to understand how they're feeling by looking at their faces and their eyes. Unfortunately, not all the people in the world are able to do that, as they are affected by some ocular pathology. It could either be glaucoma, which limits your peripheral field of view, or macular degeneration that results in a loss of central vision, or diabetic retinopathy. So this is very important also because a recent study made by the National Eye Institute highlighted how the 4 main ocular pathologies that are affecting people in the Western industrialized countries are going to affect double the number of people by 2050. So there's an increasing need for biomedical instrumentation that could allow us to detect those pathologies, and in particular we focused our work on both macular degeneration and glaucoma, as these two are treatables if they're detected at a very early stage, even though no vision loss can be recovered because the disease progresses very fast. So let's now focus on the research hypothesis on which we based our work. The first hypothesis is the one that is based on multiple studies that found a correlation between choroid pigmentation and both AMD, glaucoma, and retinopathy. And this means that the pigmentation of your ocular fundus, which is your choroid, determines the probability of occurrence of these diseases. Also, this pigmentation is directly connected to the iris pigmentation. So the two parts of the eye, the choroid and the iris, are directly connected. Actually, they are part of the same ocular structure, so they share the same pigments and optical densities across their layers. And so we decided to use the iris pigmentation to detect at a very early stage both AMD, glaucoma, and diabetic retinopathy. And this is also confirmed by other studies that were made in this field, even though they do not quantify this depigmentation, which occurs when the pathology is already progressed. And you can see from that picture at the bottom of the slide that you have a severe depigmentation of the eye. The second hypothesis connects the retinal blood flow rate and the occurrence of both glaucoma and diabetic retinopathy. This is something that is already measured in clinical practice, and but the point here is that state-of-the-art instruments are complex, they cost a lot, and they have low robustness in terms of mechanical stability and optical configuration stability. So we asked ourselves, may a novel optical instrument overcome such limitations, so reduce complexity and costs and increase robustness? To recap, the requirements of these two systems are two. So the first one is we want to measure the iris spectral reflectance to determine the pigment's concentration, distribution, and their variation during time. And that's why we decided to develop a hyperspectral imaging system. While the second point is we want to measure the flow rate of blood in the retinal vessels with a simple, low-cost, and robust optical setup. And that's why we implemented a single-arm, self-mixing, low-coherence Doppler-based interferometer. So we'll focus, I'm going to focus the first part of my presentation on this hyperspectral imaging system for the human iris. Okay. Compared to natural eye vision that is only able to detect red, green, and blue bands, so that's because our photoreceptor can only detect these three let's say wavelengths, bands of colors. We can only perceive a certain part of the visual spectrum. On the other hand, hyperspectral cameras have more bands, so they actually can distinguish more color bands, also outside of the visible range, so in the ultraviolet and in the infrared. And this allows us to collect a lot of information that are both spatial and spectral information that can be used for image analysis. We developed this experimental setup to image the iris that is based on a CMOS camera that has a spatial resolution of 11 microns on the iris. Then we have a light source that is a custom monochromator that I designed from scratch and implemented that sweeps all the wavelengths from 400 to 900 nanometers with a spectral resolution of 18 nanometers. And both the camera and the monochromator are controlled by a PC on which there's a Python program running that synchronized their behavior. In addition, I also characterized this monochromator that has an output spectrum power intensity that is quite flat, let's say, across all the wavelengths, and also the full width of maximum of these pulses is dependent on the wavelength, and it ranges from 13 to 23 nanometers. While for the program that is running on the PC, I developed this graphical user interface in Python that allows the doctor to type all the patient parameters and to trigger the acquisition of the hyperspectral cube, so all our images in the hyperspectral range. Here you can see the image, the picture of the implemented setup that is based on the camera, the monochromator, and the PC. So the patient is asked to lay his chin and forehead on this ophthalmic microscope support and to look at the fixation LED with a contralateral eye. And then the doctor can trigger the acquisition. The measurement procedure involves basically two steps. So the first step is about qualitative assessment of the iris color with respect to an iris grading scale. This scale was developed by Franzen, and that's what we did. So once you do that, you can trigger the acquisition, and what you get is a hyperspectral cube of 22 pictures that are acquired between 480 and 900 nanometers, every 20 nanometers with 20 nanometer steps. And then there's an image processing procedure that allows the user to define the region of interest, so it's the region of the iris, to normalize it with respect to a white reference standard, to filter it in order to reduce noise and highlight the spatial features, and then to extract actually the reflectance of the iris that is averaged over all the pixels in the region of interest. We also tried to measure the spectral repeatability, the measuring performance of our system. So we did that on 8 healthy volunteers, and we characterized their eye color as I mentioned before. And in this slide, I'm just reporting an example of 3 of them in order to highlight the fact that their eye color that is reported on the left gives an outcome in the hyperspectral range that is quite interesting to observe. In particular, you see that at 500 nanometers, the darker irises that have a higher melanin content absorb more, so they look darker in the image. And this is also confirmed by our experimental results, in which in the visible range, so in the blue range, so between 450 and let's say 550 nanometers, the darker irises exhibit a lower reflectance, and that's because melanin absorbs the light in that region. Whereas in the red region, so around in the near infrared region, so around 750 to 850 nanometers, there's a trend inversion. So that the darker irises have a higher reflectance, and this might be connected to the effect of melanin scattering. So the melanin granules that are present in your iris, they backscatter the light, so the reflectance is increased. Also, above 850 nanometers, you see that all the curves, they start to bend with the same slope, And this is related to water absorption that is more or less occurring at 950 to 1000 nanometers. As I said before, we wanted to quantify the measuring performance of our system, so we did that measurements over 3 measuring sessions, and we calculated the coefficient of repeatability, which is quite good over the spectral range. It is plus minus 10%, on average, it's plus minus 10% for dark irises and plus minus 6% for light irises. So to conclude, the system demonstrated to be suitable for hyperspectral imaging of the human iris. We're currently performing studies on a large number of subjects at the Ospedale Britannico in Rome, but there's still some work to be done. In particular, we need to automate data processing procedure and to develop an optical model of the iris that includes pigments distribution and their densities over the iridial tissues. And in the future, we're also interested in applying some machine learning techniques to this images dataset, so such as principal component analysis and k-means to classify and clusterize our data. The second part of the presentation involves low coherence interferometry for retinal blood measurements. So just to remind you, we wanted to measure the flow rate of blood in the retinal vessels with a simple, low-cost and robust optical setup. The working principle is based on interferometry, as I said before. Our light source is a superluminescent diode, and let's assume that this on the right is a section of a blood vessel in which you have blood flowing through it, and there are particles in the blood that are dissolved, and these particles have a parabolic shape profile if the flow is laminar. It means that the particles in the center have a higher speed than the particles on the edges of the blood vessel. The photocurrent, which is our signal of interest, is generated by the optical beating between the signal that is back reflected from the inner surface S1 and the optical signal that is back scattered by the particles that are at a distance r lower than 1 coherence length. So these optical signals are collected by the monitor photodiode. The photodiode that generates a photocurrent, and this photocurrent has a spectrum that is almost Gaussian, so it can be expressed with that equation on top, where sigma, which represents the spreading of our Gaussian spectrum, is linearly dependent on the volumetric flow rate. So it means that for higher blood flows, we expect our Gaussian spectrum to be broader. I developed this experimental setup that is based on 2 tanks filled with distilled water, and we dissolved a highly scattering fluid into the water that is intralipid at different concentration, and then with a multi-turn valve at the bottom, we were able to finally regulate the flow of the liquid in the hydraulic system. Then the pump is just used to recirculate the liquid from the bottom up. The interferometer is based on superluminescent diode, as I said before. There's a single mode fiber and a collimator that are used to shine the light on the duct, on the vessel. And then the photodiode collects the back scattered and the back reflected light. We also designed a signal conditioning electronics that is used to amplify the photo-generated current, and then that voltage is acquired with a digital spectrum analyzer. So the first thing we did was to verify that our assumptions were correct. So we verified that the spectrum is Gaussian, and as you can see, it is. And then we wanted to calibrate our system for three different flow rates, Q1, Q2, and Q3, with a fixed scatterers concentration, which is 0.06%. As you can see, for higher flow rates, in particular the blue curve, which is Q3, we actually have a broader Gaussian spectrum, so this is in accordance with our theoretical model. And by doing that, we were able to calibrate our system, and so to calculate this green line, that is our calibration curve. And the slope of this curve represents the sensitivity of our system at that particular concentration. And by doing that, we then were able to estimate the flows that were in between the minimum and the maximum flow rate that we used for calibration. The estimation was also quite good because the measurement error is pretty low, as you can see. And we repeated this same procedure also at different scatterers concentration. So we recalibrated the system for concentration of the intralipid ranging from 0.015 to 0.36%. And as you can notice, the sensitivity drop is quite low. It's about 30%, which is remarkable if you consider the increase of scatterers concentration. To conclude, the work demonstrated that low coherence self-mixing optical configuration can be implemented and exploited for flow measurements. The system is simple, compact, and easy to align, and also mechanically stable. And the most important thing is that performances did not degrade, even though we increased the scatterers concentration of about 2,400%. And in fact, as we saw before, the system sensitivity reduced its value of less than 30%. In the future, we want to design an improved signal conditioning electronics to characterize the system at even higher flow rates, and we want to apply this technique to phantom eye models that actually mimics the human eye. I want to thank you all for your attention, and if you may have questions, I will be happy to answer you. Also, I want to thank all the people in the lab that contributed to this work and that donated their eyes in the name of science. And also I want to thank Professor François Delory from Harvard Medical School, who guided us during this work. And I want to thank him also for his contribution. This is my publication list, so these are the journals, and here we have the conferences. So thank you again.
Thank you and you have a very good English. Now, question from the Commission?
Yes, just a curiosity. I've seen that you just started a test with a lot of patients,
Yes.
but I would like to know if you have preliminary results with persons with problems like AMD or so on.
Okay, so we're testing the system on patients with both glaucoma, diabetic retinopathy, and maculopathy. But we also have a control group of healthy patients. We started analyzing the data like a couple of weeks ago, so we don't have much results, but our goal is to use that spectral fingerprint to monitor during time the variation of the reflectance, so the pigmentation, and this can be used as a prognostic factor for the detection at a very early stage of those pathologies. That's at least what we expect.
Just a very quick question. You mentioned at the beginning of your presentation that the monochromator you basically designed from scratch. Is that correct?
Yes.
Okay.
Yes. Everything here was designed from scratch.
Okay. What were the limitations, the technical limitations of existing monochromators that prevented you from using an existing device?
Okay. So the first thing that we had to consider was that we wanted to have a customizable spectral range. So the monochromator actually is able to span, let's say, from 400 nanometers to 1,000 in our case, but we then restricted the value to a spectral range of interest. Also, resolution was important because most monochromators they have a trade-off between the resolution and the output power. And in this case, in the blue region at least, we need to have a high output power because melanin absorbs a lot of light. Otherwise, you acquire a black picture of the eye. And so we had to, and as you saw before, the spectrum actually has a peak in the blue region, so it's more intense over there. Yeah.
Is there any chance that this system might be integrated and miniaturized in such a way that you can, for instance, install it on a special purpose glasses and have continuous time monitoring of this?
Yes, well, when I mentioned that we wanted to use some machine learning techniques, and in particular principal component analysis, is that the goal of that would be to understand which are the most important wavelengths that you need in order to reconstruct your spectral signature of the iris. So you can also think about the fact that you can remove the monochromator and use, let's say, LEDs centered at certain wavelengths and just scan those wavelengths that are important for your purpose.
In this way, you would also save a lot of power. Maybe.
Yes, exactly, and also have a faster scan, because now it takes around 4 seconds to scan to get the hyperspectral cube. Yes.
Okay, thank you.
Thank you.
So the next candidate is Giuseppe Fiameni. The title of his PhD thesis is Big Data Management of Large Scientific Data Sets.
VGA. C'è un cavo VGA.
So,
No, è un...
Un convertitore.
Grazie. Okay. Now I have two.
so
Okay. Yep.
okay.
Thanks, Sonia, for the introduction. This is Giuseppe Fiameni. I will give you a presentation about the work that I have been doing during my PhD study. I did this activity in collaboration with Cineca. That's the company that I work with, and another European project which is called Human Brain, where I'm one of the architects of the infrastructure. So this is the outline. Basically, I've been spending my time trying to test big data technologies in scientific domains and try to understand how these technologies can match scale-out infrastructures, providing high performance capacity and capabilities. So we did some performance evaluation about deep learning frameworks that are becoming very popular now, as you have seen in the previous presentations from my colleagues. Try to exploit MapReduce technologies and techniques to improve analysis of climate data sets, coming from a very scientific domain, and the contribution that I gave to one of the pan-European infrastructure for interactive computing services. My presentation ends with some highlights about quantum computing that are also becoming very popular in the computer area nowadays, but I will keep them if I have time. As I said, deep learning has become very popular. There are a lot of frameworks available now, and but the problem is that so we have a lot of workloads, but it's not very clear how these kind of frameworks can be used to work with very large data sets and scale out even, so scale up and scale out. So scale up, trying to reach the peak of these infrastructure, very, let's say, leading edge hardwares, components, and scale out is not clear how many nodes, how much resource these frameworks can really use. So this is a sort of a convergence between big data and high performance computing. So I'm coming from the high performance computing domain, and trying to meet these requirements. So although these components, these workloads try to stress a lot, let's say systems like CPU, memory, storage volumes, and internal communications, they have not been developed to reach high performance. And so only the recent developments, just to mention one, TensorFlow, is trying to really tackle this point and try to maximize the load of these systems and try to use more multiple nodes at the same time, providing good performance. So I've been lucky because I got access to the most important systems that we have in Italy, and without going through any review, but using my personal account. So this is the test that we'd use. I've been testing normal general purpose architecture coming from Intel, Broadwell and Knife Landing for hyperscaling systems, but also GPUs like the Key 40 and the P100, the Pascal, the Tesla Pascal coming from NVIDIA. So these are the tests, the networks that we test, AlexNet, GoogleNet, Overfit, and VGG that have been quite popular recently and recognized winner for several conferences. I just put here a very high-level description of what these networks do. So these are the first results. The paper that we published in this includes all the network, but just to show you, I took this chart for the Overfit. So we tested several frameworks coming from Caffe, TensorFlow, Theano, and Neon. Maybe you don't know this, but many many hardware vendors, they do provide their own customizations. And these are not publicly available most of the time. And so, for instance, Intel has been doing several developments in this direction, trying to customize Caffe, for instance, because they are using their own low-level math library, which are not publicly available or are not open source. But they provide a very important boost in terms of performance. And but this is a very you can see the colors define the batch size, and you can see how many images per second these frameworks can process according to the hardware. If you move from the left to the right of this chart, you move from Broadwell, which is a very general purpose processor, through Knife Landing, which is a mini multi-core system, Key 40, and then the P100. So you can easily see that the P100, which is a very powerful GPU, outperforms most of the normal hardware that you can find in local regional clusters or in your lab. So the P100, the best combination, it's between the P100 and the Neon, which is a framework coming from Intel. So Intel is providing a framework that provides very good performance using NVIDIA hardware. This is a strange combination, but it's a very important result, I would say. So, and this was done using one single node. So if you have a box, a workstation, this is the performance that you can reach if you do some customization to your code. And the document that we publish includes all the customizations that we did and the tuning with the high parameter. But we went a bit beyond, because the framework that we test here were very popular when we did the work. That means 1 year and a half. But over the time, TensorFlow became maybe the de facto framework for deep learning. So we decided to extend it and to involve the ResNet 50 as a network, as a neural network, convolution neural network that we test on our Skylake system coming from Marconi supercomputing, using the Orvod library. So we are coming from a parallel, let's say, oriented applications. We use this Orvod library that is coming from Uber, to test how TensorFlow could scale out using different nodes. And we went up to 256 nodes at the same time. These are the results that we got. It's not, I mean, it's very tough maybe for you to read all the charts, but you can see there are basically two columns. So we moved from one single node to up to 256, and maybe so yeah, the color is not that nice, but on the left there is the KMP block time, which is equal to 1, and the KMP block time equal to 20. So When you go up, you have to do a lot of customization, a lot of tuning, and the document that is publicly available reports about this. And because you have to tune the time that a single thread should wait for the other threads to communicate. Because the problem of the networks is that if you want to go parallel, the only mechanism that you have is to exchange the wave of your network in a multi, let's say in a collective communication. So all the processors, all the tasks need to communicate with all the remaining tasks. This is very expensive. But the charts show that if you really want to achieve very high performance using a TensorFlow, you have to do a lot of tunings and tune your hyper parameter. There are no recipe, unfortunately. It's very tough to understand what's the best combination. You have to do a lot of attempts before reaching a good performance. But for instance, and if you move from for instance, if you use a batch size of 64, you can get up to 80 images per second processed using 16 hyperthreads. So that's a good number, especially if you want to process a lot of images coming from your data sets. But to achieve those results, you have to execute a lot of attempts and try to find out what's the best KMP time. That's time that thread should wait after completion. I mean that hypermeter affects a lot the result of your execution. Okay. But in general, we can observe that TensorFlow is very stable. But if there is not a direct correlation between the changes that you can do in the hyperparameter and the performance that you gain. So they're very flapping. So if you change, let's say, a small change in one of the hyperparameter can really provide very very bad performance. So there is not a linear correlation among the hyperparameters. So it's a sort of a magic behind this. It's not that clear how this framework actually work internally. Okay. But we know that surely Google is doing a lot of work in this direction. So we've had Google back with these results because I mean. The numbers that you obtain are not very deterministic sometimes. Okay, because there are some statistics and some let's say stochastic in input at the beginning for each execution. Okay. So we also evaluated the MapReduce, Hadoop and Spark to analyze climate data. This is a work that has been done in collaboration with the ICT and OGS, that are two centers in Trieste, collecting data coming from radar about climate changes. They do climate changes studies, and of course the data manipulation processing are two very important aspects of their work. So we try to help them trying to analyze the data that they collect, observe the data sets using MapReduce technologies. So this is the way they usually work. There are a lot of libraries in these domains trying to this is a very high throughput workload. So they collect data sets, they divide the data sets in subcubes, and then try to calculate features. So they can be the average, the max temperature, the low temperature. So this is the work that they usually do. Unlikely these libraries don't scale very well, especially when the data sets became too large. And so we try to modify a bit this serial code using MapReduce. But so most of the code gonna in a memory error because they are not able to handle large cube. even though you have a very large memory system. Okay, what we did, we used Apache Hadoop. This was a very nice case for Apache Hadoop because, I mean, Apache Hadoop promises you to scale out very well, but the problem is that Apache Hadoop was developed to process text files, chop data brutally. You don't have the control how data is chopped because this screw up a lot the file system. It's based on Java and it's a batch processing model. And but climate science, most of the time they use the binary files, especially in SCDF in the climate domain. They have monolithic data, so you cannot chop the data very easily. So you have to do that on purpose. So you need to know why. I mean, in which way to chop the data to cut the data out. We use any programming language except Java. So in the scientific world, no one is using Java. And then so climate science, if you want to get, let's say, it's an interactive oriented world. So to avoid these problems, we developed these two libraries, which are called Pipistrello and Tina. It's very fantasious names, but Pipistrello helps us to do MapReduce onto binary data sets using their own physical position on the file systems. I mean, this is a very deep customization because MapReduce try to hide you from the position of the data. And Tina, which is a very lightweight Python library that's sitting on top of climate libraries, try to handle NetCDF data on using the tool that we have been already using. So this work was published for an international conference for big data principles, architectures, and application 2017. These tools are publicly available, and these are the results that we obtained. Very briefly, I mean, if you see the two charts on the top, to the two graphs on the top, the left one was that we could obtain before the two libraries were developed, so according to the capacity of the systems that we had. So you have a very coarse-grained organization of the data. There were no smooth transition in the data sets, but the regions, so very two near close cells, there could be very large deviation of the data set, of the measurements. And on the right, you can see what we did, so the benefits that these two libraries introduce in our computation. So you can see very smooth transitions across the variables. In that case was the temperatures, so how the temperatures moves across all the region. This was done using Cordex data sets. And so we would not be happy if, okay, we had a good improvement, but that was not enough, because I mean you can achieve those results if you, let's say, put a lot of resources. But for us, the most important point was about the scalability. So how this code can scale up according to the size of the data. And on the bottom, if you can see there are two lines basically, the red and the blue. The blue, if you draw a line between these 2 points, this was the scalability before the introduction of these two libraries. So you can see that will scale very badly. And with the red, it's the scalability of the code using Tina and Pipistrello. And there are two green stars, that's the optimal one. So that is the optimal scalability that you can obtain according to the data. And then, so we are very close to be optimal. So these two libraries are very interesting, and many communities are looking at those, but of course we need support to maintain them, to keep developing it, to adjust the code. General consideration about Hadoop and Spark in a HPC context. So the big problem is about I/O. As I was saying before, the chopping of the data is it's a brutal approach that many scientific communities don't like. So if you really want to use these two to frameworks in a scientific domain oriented. You have to do a lot of customizations. We did some work, especially in managing the data in a vertical and horizontal way. The vertical is how the data move from the local disk to the RAM, and the horizontal how the data is exchanged across multiple resources. There is one promising solution which is called Taitune for the vertical data movement to optimize how the data is moved across different tiers. Horizontal, we did some tests. We customized a bit the I/O, the network I/O, trying to leverage the RDMA, which is a feature that many systems have, that allows you to easily move data across the two central memory of two different nodes. We have not been able to publish results about this work yet, but this is something that will continue even beyond the end of PhD. But I mean, Apache Spark is working a lot to solve these problems because there are very strong bottlenecks about this. So there are many groups working on this, and also large vendors, hardware vendors. Okay. We did some tests, and accordingly to what we have now, Apache Spark is not able to scale. Up to order of magnitude of 100 cores. So 100 cores, it's approximately less than 8 nodes. If you have an hyperscaling system. So if you want to really try to compute something, and then you want to use a Spark in a context which is larger than that number, you might face a lot of problems concerning the I/O to the data. If you of course pump a bit the hardware, you can go up, and then but we believe that Spark could not reach more than 10,000 cores, which is, let's say, a small-scale system. Finally, this is a work that I've been doing in an European project, which is called the Human Brain. I was being involved as one of the architects of this infrastructure, because the idea, is to provide computational and storage capabilities to the neuroscience community. We had to integrate several systems in Europe from the main HPC centers. I was driving from the Cineca corner, of course, but we developed several services and favored integration of these systems to allow the neuroscientists to get access to this capacity, to this storage, to these resources pool. And so we ended up with this infrastructure that is now available, which is called Phoenix, that provides at the European level different services in a sort of cloud-oriented world. So moving from the infrastructure to users, so users can plug their platforms across on our HPC resources, and with the several connectors. They can consume and fetch data from the systems. These are the services that we provide. Computing data and federation is very, let's say, straight organization, because we provide interactive computing services, cloud, and of course data management. So I took the opportunity to show you, this is one of the simulation that this infrastructure is currently running. I hope it starts. No, it doesn't. But anyhow, I'm sorry for this, but I don't know why it's not starting. No, it's not working. So this is a simulation that we launched that we launched in our system. This is the simulation of a olfactory bulb. So it's a 3 millisecond simulation. So it's a simulation that we use to simulate how the olfactory bulb works when it receives some inputs. And to do 3 millisecond simulation, we spent more than 40 million core hours. So this is a job that ran for 40 million core hours on our systems to produce a simulation of 3 milliseconds. So the goal of this project is to simulate the human brain activity, so you can imagine how many resources will be required to do that at a very large scale. It was nice, but unlikely it's not working. So, okay, this is the list of publications, the conferences, and the teaching that I've been doing over my 3 years thesis, the PhD program, and yeah, thanks.
So, for the topics, I can some question from you related to the platforms of data analysis or the Spark limits. Okay.
Well, actually, I have a curiosity.
Yep.
I mean, you mentioned that better hardware would be very desirable, which is a very general statement. And we know that HPC, I mean, is there any interest, is there any analysis, any prediction of what the power consumption, the overall power consumption of these systems that should simulate the behavior of a working human brain would be? Is that affordable with the current technologies? Is a European network enough to carry out the job, or should we wait for a revolutionary, let's say, hardware to do that?
Yeah, this is indeed a good question, because the power consumption is a cap on how these systems can go up. Currently, one of the systems, I mean, every system that is participating to this network can consume up to 4 megawatt, and providing a peak performance of 20 petaflop. We are now designing a new system for an initiative which is called Euro HPC, and because we are going to provide a system in Italy, the ambition is to have a system in Italy that can rank, in the first 3 in the world in the 2020, and that will be up to 20 petaflop with a maximum consumption on 9 megawatt. And but there are a lot of works in this direction now to reduce the power these systems work. There are some specialized hardwares to do, like the ICT, for instance, that we have been using for the deep learning, that they have very low power consumption, but of course, the less you consume, the less flexibility you have on your system. This is a very generic rule. And but I mean, we are working on how to optimize the use of the resources, because in terms of power consumption, there will be no breakthrough. I mean, we don't envision any breakthrough. So quantum, it's a big promise. I mean, the quantum computing can really completely change the paradigm, but it will not be efficient and effective before the 2035. So there are still more than perhaps 20 years ahead, but that will come.
We have another question.
Giuseppe, just my question is related to the industrial application of your work, in particular of the technologies and Spark. There are some industrial application or some commercial system using such technologies?
So we have, this is outside, let's say, my PhD activity, because we do have a work with a company doing drug designs. And you know that now drugs are simulated. So all the drugs that we have, all the medicines that we have, they are all simulated. We have a work with an Italian company that tried to simulate 9 billion compounds. So they try to do all the simulations, so now the virus can be folded in a chemical compound. And we ended up with a database of 9 billion lines. And now they want to do, okay, they want to process data. We are looking at Spark to do that and try to filter out. We can filter data in a 2D matrix of 9 billion lines. There are some attempts, some let's say some experiments that we are doing in that direction, but we still don't have a very stable system for that. But there are few applications that are coming, surely. Thanks, Sonia.
Thank you, Giuseppe. The next candidate is Paolo Latorraca. The topic is completely different, development of thermoacoustic loudspeakers. Paolo, what do you want? Probably la chiavetta has to be put...
Okay. Thank you, Professor Bergamaschi, for the introduction. My work is actually titled Modeling, Characterization, and Development of Thermoacoustic Loudspeakers, but probably it was too long for the flyer. And okay, no problem. My work was supervised by Professor Paolo Pavan and Professor Luca Larcher. So let's start from the device, the thermoacoustic loudspeaker. You can see two thermoacoustic loudspeakers over there, and they are electroacoustic transducers, meaning that they convert an electrical signal like a voltage into a pressure signal that can be perceived as sound, exploiting the thermoacoustic effect, that is the coupling between the temperature field and the pressure field in the air. Those devices have a very simple structure, as you can see. They are made of a solid substrate made of an electrically and thermally insulating material, and an active film that is, let's say, stimulated by the voltage signal. The active film must be conductive, electrically conductive, and must have a very low heat capacity. This is typically, let's say, historically done using very thin metallic films, but I found out, let's say, a better way to do that using conductive random networks. Yes, these kind of structures that are nanostructures enabled by the recent advancement in nanomaterials and nanotechnologies can be made using different kinds of materials like metallic nanowires and carbon nanotubes. They retain the metallic-like electrical conductivity while having a much lesser content of matter in them. They achieve a much lower thermal conductivity than a solid layer of metal. In collaboration with the University of Munich, I fabricated thermoacoustic loudspeakers using spray coating of nanostructural materials. We used carbon nanotubes, we used silver nanowires and copper nanowires to spray coat different substrate with those materials. Here are some samples of those thermoacoustic loudspeakers made with silver nanowires on the top and copper nanowires on the bottom, either on glass on your left, and on Kapton, that is a polymer, a flexible polymer on the right. As you can see, the devices are transparent and they also are flexible, and they work also in bent condition, in bent configuration. On the right, you see the electroacoustic characterization, so the pressure response of those devices under the bent configuration you have on the top. And they always work, also in band configuration. Okay, the next step was pretty much unknown. I didn't know what to do next to improve this kind of technology. So I decided to build a model of those devices in order to drive in some way the development. I recognized two atomic transactions in the operation of those devices. The first is an electrothermal transaction, that is the voltage to power conversion due to the gyrating happening in the active film, and then the subsequent distribution of the heat between the substrate, the active film, and the air. And then there is the second transaction, that is the proper thermoacoustic transaction, in which the heat injected into the air makes the air expand, generating a pressure wave. You may notice that the first transaction, the electrothermal transaction, is nonlinear. But I prefer to, let's say, building the model, I prefer to neglect this nonlinearity for three reasons. First, I prefer to work with linear model. I believe anyone would prefer to work with linear models. Second, the nonlinearity gives no information about the optimization, okay, what can be done to optimize this kind of devices. It's just a nonlinearity. And third, this nonlinearity must be compensated, must be eliminated in some way, because this kind of nonlinearity is not acceptable for audio applications. So my model is more or less something like this. The electrothermal transaction was quite easy to model. I just balanced the generated heat in the active film with the heat distribution between the various parts, considering the heat accumulation effects, conduction, convection, and radiation. The only tricky part was the modeling of the substrate that has a frequency-dependent thermal behavior, if you want. They behave at low frequency like a heat capacity, and while at higher frequencies, it becomes like a semi-infinite medium for the thermal wave, so it must be described by thermal effusivity. But anyway, the model fits very well the experimental result, and you can see clearly this is the thermal frequency response, so the frequency response of the temperature, of the surface temperature of a thermoacoustical speaker. You can see the shift from a minus 20 dB per decade in the response, that is typical of a heat capacity, and it shifts to a minus 10 dB per decade, that is typical of a thermal effusivity. The thermoacoustic transaction was a bit trickier to model, because I have to couple the wave equation, the pressure wave equation, with the heat equation. So it's a non-adiabatic wave equation, quite complex. There is no closed solution for arbitrary shape of sources, of the source. So, but let's say that with some smart mathematics, it's possible to obtain a solution in this form, where the information about the transaction, I don't have a pointer, but which is the first part. Sorry? Okay. This part that describes the transduction is separated from the part relative to the propagation and to the, let's say, while all the geometric parts are encapsulated in a directivity function, more or less like for an antenna. Combining the two transduction, I obtained the full electroacoustic transaction that fits quite well the experimental results. And from this, I noticed that the only thing that can be done to improve the efficiency is to reduce the thermal effusivity of the substrate. So I looked for low thermal effusivity materials. I found out that the most promising materials are nanoporous materials for two reasons. First, they have a very high air content, and the air is low density and has a low thermal conductivity that are very useful to achieve a low thermal effusivity. And second, the confinement of the air into, let's say, a nanoscale structure makes its thermal conductivity even smaller due to the Knudsen effect. Nanoporous materials that are available are, for example, the aerogels. Can be silica aerogel, is the most famous. Also carbon aerogels are available. And the polymeric nanofoams are also start to be available. I decided to focus on silica aerogel just for its high availability. Using silica aerogel, for example, the model predicts that there should be an improvement of about 20 to 30 dBs with respect to the glass and the Kapton. So I tried to use silica aerogel to fabricate a thermoacoustic loudspeaker using spray coating, but this was a complete failure because the aerogel is unfortunately hydrophobic. So it cannot be easily processed with liquids. And so it cannot be processed by spray coating. We tried to remove the hydrophobicity of the surface of the aerogel using plasma treatments, but then the aerogel became even more fragile, and also the nanowire network was extremely fragile. It was impossible to characterize this kind of samples. So I decided to use spatter coating to deposit a gold layer on the aerogel to test if at least this kind of concept works. And indeed it worked. You can see there is an improvement, the improvement of 20 to 30 dBs predicted by the model. And yes, this is the first thermoacoustic speaker made of aerogel, silica aerogel, and as far as I know, this is still the best thermoacoustic speaker fabricated using a solid substrate. So let's get back to the nonlinearity that must be compensated. It is clear that the voltage to power conversion introduces a distortion that is measured in the audio field using the two metrics, mainly the THD, total harmonic distortion, and IMD, intermodulation distortion. Maybe you are familiar with those metrics. However, this distortion must be reduced as much as possible. Techniques that are proposed in literature don't do a very good job at the moment. The most common technique used at the moment is simply to add a DC voltage to the audio signal and try to leverage on the squaring phenomena to arbitrarily reduce the nonlinearity, the total harmonic distortion. But you can in fact reduce very much the total harmonic distortion, but at the same time you are increasing even more and more and more the working temperature of the device. So you always have a trade-off, and this is not the best approach. So my target was to develop a driving technique that perfectly compensated the nonlinearity while minimizing the working temperature of thermoacoustic speaker. My solution was to use an adaptive digital predistortion applied in the digital domain to the audio signal using digital signal processing techniques. The idea is simple. The voltage to power conversion applies squaring to the voltage signal, to the audio signal. In the digital domain, I wanted to apply an inverse nonlinearity, that is the square root. Unfortunately, the square root cannot be applied directly to an audio signal because the audio signal has a positive and negative values, and while the square root must have a positive argument. So I added a voltage shift, but this time it is not a fixed voltage shift, it is an adaptive voltage shift. And this allows for the modulation of the working temperature of the thermoacoustic loudspeaker. This adaptive voltage shift must be designed following two constraints. First, it must follow the envelope of the audio signal in order to ensure the positivity of the square root argument. And second, it must be band limited below 20 Hz in order to avoid introducing spectral content in the audio bandwidth. And this technique works very well. Here is the characterization of the total harmonic distortion, intermodulation distortion. You may notice that there is no sign of harmonic distortion, and there is only a very small intermodulation distortion. The metrics are measured 0.46% of the total harmonic distortion and 0.18% of intermodulation distortion are perfectly fine for audio quality applications. Finally, here is the characterization of the temperature, of the working temperature of thermoacoustical speaker, comparing a static voltage shift with the proposed adaptive shift. And you may see that there is always a reduction of temperature, but the reduction is dependent on the, let's say, the typology of the audio signal. This algorithm is more effective for impulsive audio signals, such as a drum, let's say, because it requires the maximum voltage shift only for a short amount of time. So to conclude, during my PhD, I've contributed to different aspects of the thermoacoustical speaker technology. I've introduced the fabrication of thermoacoustical speakers using spray coating of metallic nanowires. I've developed a new model for the description of the thermoacoustical speaker as a device and used it to further improve this technology, okay? Developing a silica aerogel thermoacoustical speaker. And finally, I've developed these new driving techniques that successfully linearize the device while minimizing their working temperature. Here are the list of publications. Those are publication on journals and publication, let's say, conference and a submitted article. Thank you for your attention.
Thank you, Paolo.
If you have any
Questions?
I'm sorry, I have a problem with the last graphs that you showed. Can you go back to that?
Yeah.
Because it's not really very clear. Here we have two graphs with essentially the same vertical and horizontal scales, okay? One is produced surface temperature versus time. One is produced by a drum, so impulsive. So I kind of think,
on the right, on the one on the right. Is.
I kind of think, you know, you beat once on the drum. So of course the acoustic impulse is shorter.
Yes.
I assume this will cause a smaller temperature rise, which I see there.
Yes.
Okay, and then why it stays stable for such a long time, which is comparable to the one of an acoustic guitar, which is probably causing an... So it seems that there is a hidden parameter here, which is
simply
the
the
actual
signal
power or duration of the signal.
Is a series of impulses. So it's 77, if I remember well.
So the drum is not one impulse,
no,
but
no.
Playing dun like this.
It's a drum track.
Okay, but then to make a fair comparison, shouldn't you weight these two curves or graphs in some way by the let's say the effective power? Shouldn't you calculate
of course,
because there will be enough time in that.
I see
so
did
you
your
account for this in?
No, for me it's quite obvious that of course if the input signal requires more power, the temperature will be the same. It's clear. But here I want just to show that let's say this property of this kind of algorithm that If you decide to use it for some kind of signals, it behaves better. If you want to use it on, let's say, white noise, it will be quite a disaster. Okay, that's it. That's the point.
Okay, thank you.
Thank you. The next candidate is Luca Magnotta. The title of his PhD thesis is Data Integration and Analysis Tools. It's the first industrial PhD of our ICT doctorate school. So probably his presentation is a little bit different from the ones of the other PhD students.
Good morning, everyone. I'm Luca Magnotta, and I'm here to discuss my doctorate thesis about analysis and development of advanced data integration solution for data analytics tools. And I want to thank Professor Bergamaschi and Professor Beneventano, and Data River, that is the company I work for, as responsible for the data integration unit. In fact, in Data River, we have the mission of integrate business data of the companies with external information coming from big data, market analysis, social network, open data, and so on. And discover the information that are hidden in this data, and to give an information integrated and updated in real time to understand the value of data, to a unified view of integrated vision of the data sources, with the goal to improve the decisional, production, and provisional process with an optimization of cost and then time. In fact, data integration nowadays is a big deal, because modern enterprises are often organized in virtual networks, where the enterprises operate through inter-enterprise competitive processes. So it produces a problem of heterogeneity of data, of distribution of data, and they have to be put together and integrated to build a shared and integrated knowledge base. And so the data integration can be used in every field, from the industry to the clinical research, to the public administration, to the finance, and also the web. And my work in this research verted on the first three topics. The first is the industry, in particular Industry 4.0, where data integration was used for solve problem of remote failure monitoring or maintenance, and allowed also the improvement on production efficiency and monitoring and analysis of information, like also the power consumption, to better use this data to optimize production. For instance, we can see a real architecture where we have a network of devices, each one that have a series of sensors that have to be integrated together and integrated also with other data sources like customer data, application DB, for example, the CRM or the ERP. And this architecture brought to the Smart Mall project, where the challenge was the design and development of a web platform for the collection and management of big data produced by sensor, to get a real-time monitoring of the whole production cycle and the analysis of the data collected, to have information of the history of the production cycle in order to optimize the maintenance of the devices. The solution is the Smart Mold web platform that allowed to get an historical analysis of the machine data, the optimization from the maintenance service, the implementation of preventive maintenance policy, and also, as I said before, the integration of data with the other application, for example, the ERP. The result of the integration is creation of a new range of products and services, and the optimization of the maintenance processes thanks to a timely alarm detection and the detection also of early signals of breakdown and failures. For example, in this figure, we can see how the data are geolocalized, and we can get information about the failures and the real-time monitoring. Another field is the clinical research, where data integration was used to build a solution for the clinical studies monitoring, where doctors, centers, and sponsors have to monitor how the trial are going, to get also the trend of the trials. Another field is the pharmacovigilance, that is the activity of monitoring the medical drugs. To do this, the integration can be made with ADC platform, that are the electronic data capture platform, or also social media to give a new set of information and KPIs that can be used for have a better understanding of medical drugs. And another application is the implementation of register of pathologies of rare disease. That is the example of the figure, where we have to integrate information coming from ADC platform, different, the one online, the one that was used before, the historical ADC platform, and also databases that has laboratory data and pedigree family chart. The challenge was to use big data to analyze these clinical and molecular data to better understand the evolution and the heredity of a disease. And the registry, we realized, allowed the research and analysis and extraction also of the clinical and molecular data for the collaboration of information exchange in biomedical and clinical research, and allowed the big data, with the big data analysis, the increase of information of individual samples, respecting obviously the compliance at the international guidelines. The results obtained are the geolocation of the enrollment and the creation of a new set of KPI to know and monitor the phenotypes related to a disease, and the possibility to identify new genetic and environmental factors that can be used for diagnostics and prognosis. Another field of the data integration is the public administration, where data integration allows to evaluate service provided by public administration at national level, but also at local level. The analysis of investments also, and the service customization. To do this, it is necessary to integrate information coming from different data sources. For instance, we can see the integration of data coming from demographic application, from user service application, and buildings service application, to build a unique knowledge base that can be used and queried. To be more precise, this brings to the PA platform, where he had the challenge to improve the territorial services provided to the citizens, to the professional, and to the organization. And the solution we realized allowed the search for the concept contained in the data sources to build a specific ontology for the public administration. And this knowledge base can be published as a web service, giving the possibility to be queried by common API. For example, it can be used also in a business analytics application to get information about investments, as we can see in this image. But other results are the measurement of the quality of life of citizens, the evaluation of topology of service provided, identification of factors that influence usability, and the verification of administrative anomalies, and in general, improve the data quality. To do this project, my research was worked on 4 tools for data integration. The first one was Momis, that is the open source data integration system realized by the University of Reggio Emilia and Data River for the integration of heterogeneous data sources. And in my research, I had to integrate it with other tools, Norms and Sparker, and apply it in a big data context. The second tool I had to use was Norms, that is a tool for the standardization of schema labels. And my activity was the integration in Momis, and doing this, enhancing the normalization logic. The third tool I used is a Sparker, that is the tool used for entity resolution. And also in this case, I had to integrate it in Momis in order to generate a relationship based on the content of the data sources. And last, I had to develop the Momis dashboard, that is the business analytics tool that is used for visualized content coming from integrated data sources that can provide dynamic views. And in my research activity, it was re-engineered and migrated to a new framework in order to improve performance and facilitate the code maintenance. Putting all together, we have the Momis framework that is linked to the Norms and Sparker plugins and communicates to the Momis dashboard to provide dashboard from the data that have to be integrated. The Momis integration system, as I said before, is the framework designed for the integration of structured and unstructured data sources that use semantics to build a common knowledge base. Briefly, the process of data integration is made up of 4 phases. The first one is the source acquisition, where are defined the sources that have to be integrated, and that there are structured information about the local schemas. The second one is the annotation of the local schema, where for integration, I want to say the process of give a meaning to each label that is inside a schema. And to do this, we use a common ontology based on the online vocabulary WordNet. Once the annotation phase is completed and each label has its own meaning, the system can extract the relationship based on these semantics. So we can see if a term is a synonym of another, is a broader term of another, or is in a simple relation. And this semantic relationship can be of four kinds: lexical, structural, designed by user, or interfered, if there are other type of link. At last, we have the fourth phase, that is the global schema generation, where thanks to clustering algorithm, the global classes are generated, and so this brings to the creation of mapping tables that describe the rules to get the data from the local schema to the global virtual view. In this way, MOMIS produces a virtual system that can be queried as it is a normal DBMS using normal SQL syntax. MOMIS has proved its efficiency, and it is used in each of the projects described before. But it was enhanced with the integration of other tools. The first one is the norms. That is a tool for the normalization, the standardization of the label. In fact, several data sources we analyzed contained a lot of terms that are not contained in the domain glossary. For example, data sources are full of abbreviation, like the acronyms, compound noun, or compound noun containing abbreviation. So this term can be annotated because annotation is based on a vocabulary, but if a vocabulary has not these terms, there can be annotated, obviously. To do this, we realized norms that allowed the normalization and the interpretation of these terms. So desk becomes description, ECDO becomes International Classification of Disease for Oncology, subject ID is split to subject and ID, inst ID is split in institution and ID. And what I have to do in my research activity is the migration from Adobe to MOMIS. Moreover, it was enhanced adding an optional man-in-the-middle approach. And to doing this, there were added some features. The annotation of verbs, because the normalization is based on the knowledge of the hypernym of each term. And for verbs, this operation doesn't work before. And two, the use of domain ontology as word dictionary. In the first one, a term like isto was untaggable, was unrecognizable. With the new version, instead, it was recognized as an abbreviation of histology, and so it was possible to normalize the term. And at last, there was the definition of specific labels for the non-dictionary word normalization. In the first version of this tool, a term like receipt acknowledgement, right in this way, it wasn't normalizable. And in this version, instead, it's possible. The second tool that was integrated in MOMIS is Sparker. Sparker is a solution for the entity resolution based on Spark that allowed to get the entity resolution. That is the task of identify different representation of the same word entity. For example, if you have these two tables, the source A and the source B, we can see that all have a name, an year, and an address, but they are defined in a different way. Entity resolution can get the similarity between birth year and year. That in one case is described like 1985, in the other case is 85, but due to the proper clustering techniques, it's possible to get this similarity. And the integration of Sparker in MOMIS allowed to define a new kind of relationship, the instance-derived relationship. In fact, in this way, MOMIS can get the relationship between location and address that are synonym, and between birth year and year. The last tool that was used is the MOMIS dashboard. That is the business analytics and intelligence tool designed to work together with the MOMIS dashboard, with the MOMIS framework. In fact, it uses MOMIS like it is a data source, a relational data source, and it's able to query it to get the data necessary to create KPIs. Thanks to the integration with MOMIS, it has a virtual approach to the data. The data resides on the local sources, and they are not loaded on the machine where MOMIS dashboard is running, like it would be done by an ATL software. And also, it has secure access to the data that are used to create and visualize key performance indicators that are in form of map, charts, and tables. And in my activity, I had to migrate it from the Smart GPT framework, that is a framework created by Google, to the browsing framework. It is a framework that allows to create a web application like they are the simple desktop application. In this way, there was a improvement of performance and browser support, and they were merged the version of the MOMIS dashboard. In fact, with the old framework, we added the two versions of this framework, one for the desktop and one for the mobile, that was published like an app. So there was an Apple version, Android version, and on the other end there was the desktop version. With this new framework, it was merged, and a single version can be developed and used. So it increased also the maintainability of code, and it has a great performance gain and responsiveness. We calculated up to 10 times in certain cases. And so, in my work, I find out that data integration is a fundamental tool to the implementation of good business analytic system. And we used solutions that are merged together, but that can be used as a standalone application. And in the future, each of these four technologies will be improved. MOMIS, for example, to the image integration and multimedia search, or to the support of scalable joins. Norms will evolve to self-learning logic for the automatic identification and better identification of non-dictionary words based on the user habits, the designer habits, and increasing, and also to the increase of the context-aware normalization. Also, Spark as a development for a new data fusion method and detection of join attributes, and also MOMIS dashboard. These are my publication and conference, and that's all. If you have some questions, let me know.
Luca, no question because the time is over. So
Sorry.
Thank you. So now we begin with the doctorate student of the 32 cycle, and we have. I need this. Davide Abati. The PhD students are Davide Abati. Davide, you are here? Yes. You have 10 minutes. And we have Federico Bolelli.
5 minutes. I tuned the presentation for 5 minutes, but I can't.
5 minutes? Yes. Very good.
Is that fine for you?
Very good. We have time for questions.
Okay, so my name is Davide Abati. I'm advised by Professor Rita Cucchiare, and I will talk about a technique we developed, which is called latent space auto-regression, and we employed it for novelty detection. So let me just briefly discuss what novelty detection is in the first place. So novelty detection is the task of identifying everything that shifts significantly from a training set of normal examples. And this has lots and lots of applications in video surveillance, for instance, in industrial defect and fault, defect detection and fault prediction, as you know, and is also emerging as an enabling factor for research in active learning and reinforcement learning, for instance, for curiosity-driven exploration. So bottom line is a very, very important problem. And this is the formal view of the problem, in which we have a binary classification task, but there's this peculiarity that we don't have the negative class in the training set. So we just get to observe normal examples in the training set, but we still have to distinguish novel examples in the testing set. So it's a semi-supervised setting, and most literature, at least in vision, in which we have large input spaces such as images and videos, rely on a parametric compression and reconstruction of normal data, and this is motivated by the fact that novel examples would lead in the test phase to higher reconstruction errors. So most works employ deep out encoders, and this is our proposal, which is also based on a deep out encoder, which is represented in the top region of the image. We have a standard encoder F, a standard decoder G, and the first part of the objective is the reconstruction term, which is standard for autoencoders. But okay. So you can see here the standard reconstruction term, and but this objective is actually regularized by an additional term, which we call the log likelihood term, and it works by means of an additional module, which is this one here, which we call the estimator network H, that tries to learn the probability density distribution of latent vectors. And before explaining why this makes sense for novelty detection, I will just briefly mention how can we make sure that this network here is actually estimating a density. So this is where autoregression kicks in. So we can think to a latent variable instance as a joint assignment over d variables, in this example here, 4 variables. And autoregression is a very well-known technique for factorizing distributions, so using the chain rule of probability. And the way it works in our proposal is that you pick an order in which to observe variables in the latent representation, and you observe the first variable and you make a guess. You take a guess on the distribution of the next variable. Then you observe the next variable and you take a guess on the distribution of the following variable in the chain, and so on and so forth until the end of the chain. Once you get all these guesses, you can apply the chain rule of probability and get a proper estimate of the joint assignment. And this sequential process, which is indeed sequential, as I explained, can be made parallel in deep neural networks by means of weights and parameters masking in the estimation network. So, but this is the actual reason for regularizing the objective the way I shown, because this formulation can be decomposed into different minimizations. So we have H, which is the estimation, the approximate density that we are approximating, and if we call P star the true density spanned by latent vectors, this formulation minimizes the KL divergence here between these two distributions. So we make sure that our approximation is actually a good proxy for the true distribution, but we're also minimizing the differential entropy of the true distribution. So this makes sense in that if you think to the encoder as a source emitting symbols, you would expect in the presence of normality to observe a boring process in which you observe more and more of the same. So in this way, we focus the encoder to capture only highly redundant features. So this is what I mean. So this is a standard data set for one class classification. This is the most normal, the normality captured by the model and the abnormality captured by the model. This is also true for natural images, and led to basically state-of-the-art results for one class classification. We also tested it, and I finished in surveillance settings in which you have the normality, which is described by people just walking around and wandering, and in the test set you have strange things happening, such as bicycles entering or vans or brawling starting. And yeah, we didn't outperform state-of-the-art, but we reached state-of-the-art. But we made fewer assumptions. So we made no assumptions about the surveillance setting. On the contrary, other competitors in this table make strong assumptions on the nature of abnormality. So we're kind of happy with that. And I think my time is up, so I will leave future works for next year's DDAY, I would say. So thank you.
You didn't show us if you have some publication on your work.
Yeah. I mean, this technique I've shown is actually under review for the International Conference of Computer Vision and Pattern Recognition. It got I would say, rather positive results in the first round, but we're still waiting for
the second round.
Yeah, for the second round. And this is the first publication on this topic. In the first year, I worked on other stuff that I didn't mention today, but I have some publication on that stuff.
So thank you. Next candidate is Federico Bolelli. And then Elena Cipressi, so if Elena come close to here just to, and probably we can work in this way. When we are asking questions, the other candidate come close to the.
So, good morning everyone. My name is Federico Bolelli and I'm pursuing my PhD under supervision of Professor Costantino Grana on the topic optimization of binary image processing algorithm. I focused the first part of my research activity on the problem of labeling connected components inside binary images. It is an algorithmic application of graph theory which aims to extract objects and their statistics inside binary images, and it aims to produce a auto-symbolic image in which all pixels belonging to a single object are given the same label, typical an integer number. And it is useful. It is a fundamental post-processing procedure for many computer vision algorithms to get final results, ranging from medical imaging to video surveillance and so on. So that's why it's important to have an efficient implementation of such a kind of algorithm. So differently from many other computer vision tasks, CCL has an exit solution that should be provided as output. And so the main difference between different implementation is the execution time. And even though the computational complexity of such a kind of algorithm is proven to be not less than O of n, there are a lot of ways to optimize this algorithm, such as using hardware acceleration both on CPUs and GPUs, or designing specific algorithm that allows to reduce the average number of memory accesses, which are the most expensive operation when performing CCL, or taking advantage of instruction cache. I've explored all these strategies in the last 2 years, but for time reason, I will give you just a brief summary of the last sequential CPU algorithm I've designed in the last year. It's called Spaghetti labeling, and it tries to merge many state-of-the-art paradigms that I studied and developed in the last years. First of all, it exploits a block-based mask scan, which scan the image in a raster fashion. The advantage of using an enlarged mask is to reduce the memory accesses because equivalencies inside blocks between pixels are already solved, and preserving the final correct result. The second optimization is the use of optimal binary decision tree. So when you check the value of pixel in the neighbor of a block or a pixel inside the mask, using an optimal decision tree, you can reduce the average number of memory accesses, avoiding useless check. The third step is to apply pixel prediction, here shown with the simpler version of the mask for space limits. So the idea is that when the mask moves from one pixel to another inside the image, some of the pixels remain inside the mask. So if you have checked them in the phase before, you don't have to check them again. From an implementative point of view, this can be achieved starting from the original optimal decision tree and pruning the nodes which don't need to be checked. And in the execution flow, when you reach a leaf, which corresponds to the action to be performed given the pattern of the pixel inside the mask, you have a goto, which brings the flow to the next tree. So the result is a forest of decision tree merged together. And that's why we call this algorithm spaghetti. The last but not least optimization is the code compression. So looking at the assembly code, we notice that the compiler optimizer tends to merge pieces of code which represent subtrees into a single code. So thanks to that, we noticed that inside the forest there were a lot of subtrees, equal subtrees. So with a more consciousness procedure, we transformed the original decision foreign into a directed acyclic graph, rooted directed acyclic graph, and this allows to significantly reduce the memory footprint source code, thus taking advantage of the instruction cache. And this is the visual representation of the final DAG of the algorithm. Of course, the code is automatically generated. It's unfeasible to do it by hand. And now I'm working on a framework which is capable. The idea is to build a framework which is capable to automatically apply all the aforementioned optimization to all that image processing algorithm that can use a mask to achieve the final result, such as thinning or chain code or also mathematical morphology operators. And the idea is to build up a simple scripting language that enable the user to define a scan mask and a bunch of rules from which generate all the previously mentioned optimization. And of course, the frameworks will be able at the end to generate the C++ optimized code for the given rules. It now works for CCL and thinning, so I plan to extend it to other algorithms. So this is the list of selected publications that mainly link to the core of my research activity, and these are all the others. Thank you.
Federico, I have 3 questions. Why to optimize a linear algorithm? First. Second.
Why?
No, second, I have 3. Second, you devise a subset of similar parts, similar trees, in order to compress and the third one is why C++? Why not C?
Okay, so the first question was why to optimize a linear? Okay, so as I said in the first slide, it is a very used algorithm, so it is quite good to have a fast implementation. So it's linear, but you can exploit hardware optimization or other strategies such as memory accesses and so on to improve the performance. The second question was about the subtrees.
Yes.
So we noticed that in the final decision forest there are equal and also equivalent subtrees. Yes. So merging them together can significantly reduce the source code of the final algorithm. So these don't change the execution flow, but reducing the code, you're able to better fit in instruction cache, thus improving performance. And the third question,
why C++?
Why not?
No. Why do you need objects, classes?
No, actually, you're right. The final implementation actually does not require classes, but we developed a framework to measure performances, and this framework is templated on the union find solving algorithm, which is one of the core part of the connected components labeling. So C++ allows how to build a more clean framework. So that's why we choose.
Thank you.
Okay.
sembrava la limitazione.
No, no, no. Good morning. My name is Elena Cipressi and I belong to the industrial application of ICT. I'm doing my PhD in a telecom service assurance company named Empirics, and the title of my presentation is Quality of Experience Towards 5G Networks. So today I would like to discuss the main research activity that I have carried out during the last year that mainly focuses on the analysis of the end-to-end quality guaranteed by voice over LTE. So as 5G promises to shift the network paradigms from network centricity to user centricity, the study of the quality of experience has become a crucial and complex research area. So the voice over LTE assisted by wideband and super wideband codecs is the best candidate to perform high definition calls and to ensure high quality in a total IP-based scenario. For these reasons, we decided to concentrate on this service, and we examined several millions of VoLTE calls, precisely 20 millions of VoLTE calls coming from a real commercial network that employ two popular speech audio codecs, the adaptive multirate and adaptive multirate wideband, in the proportion that I reported in the slide. So we took an actor perspective and we focused on the effects that different values of packet loss rate and maximum jitter have on the quality of voice call. And in the operating condition of Empirics, we deal with the passive network monitoring, and we relied on VQMON, which is an objective, non-intrusive tool adopted by the company to assess the call quality. The output of this model is the so-called rating factor, R factor for short, a number between 0 and 100 that represents the overall call quality. For the wideband codecs, the R factor has been recently updated, taking values up to 129. This work was particularly useful because we dealt with several limitations that the model exhibits that are object of future investigation. Just to name a few, it doesn't deal with the super wideband codecs, and it broadly considers the edge device approximating every edge device in an equal way by implementing a jitter buffer emulator. So these are the main major findings of this work. So this plot represents the relationship between R factor as a function of packet loss rate and maximum jitter. So as you can see, the adoption of the wideband codec guarantees higher R factor values and leads to a less pronounced dependence of it on packet loss rate and jitter maximum. As a matter of fact, since we have dealt with a real commercial network, the lack of points in the region of high values of packet loss rate and jitter maximum suggests that we have dealt with a well-designed LTE network. However, both figures demonstrate that the packet loss rate most significantly influences the end-to-end quality of voice over LTE calls. And for these reasons, we decided to better investigate this aspect. So we decided to better investigate the relationship between R factor as a function of packet loss rate. So I don't want to enter into the numerical results. If you are interested, we can discuss it offline. But by visual inspection, the exponential fit is truly satisfying for the narrowband case, while the situation is pretty ambiguous for the wideband case, where the linear choice can be seen as adequate as the exponential one. these are the list of the outputs and achievements that I have to obtain for this research activity. And now, just to conclude, I would like to introduce the research activity of the current year. So, as I mentioned before, in the context of passive monitoring, the model that we have employed exhibits several shortcomings. So, the current research activity builds on what I have discussed before. So, there are another important aspect that is crucial for the forthcoming advent of 5G networks, that is the widespread adoption of the call center, the services offered by call center. So during this year, I'm working on a novel approach based on machine learning to assess the listening quality. And in so doing, I am exploiting a proprietary product of empirics named Hammer, that is a generator of voice over IP calls. So the purpose of this research activity is to build a larger data set that contains different task profiles that are generated in this moment by a network emulator environment, and correlate each of these task profile by the judgment made by a pool of listeners. I have concluded, so thank you very much for your attention, and if you have any question, please don't hesitate to ask. Thanks.
We have a question.
Actually, a curiosity. You showed that maximum jitter does not degrade too much your quality.
It seems not.
So is it a specific feature of the 5G, or is it true also for previous? And if so, do you have a simple explanation for that?
We know that the 5G traffic is not already 5G is not already developed. So we decided to explore an LTE network because in the forthcoming advent of 5G, the mobile broadband services like the voice over LTE will be one of the best candidates to be adopted by 5G. So we took the data from a real commercial environment, and we saw that these data were pretty good, or they demonstrate that the network works very well. So in this particular data set we have examined, the jitter maximum seems not to affect, but we can say that it could be a general statement because we have leverage on very large data set. Generally speaking, and starting from the trial that I am doing, the packet loss rate seems to affect more than the jitter maximum.
At the moment is an empirical observation on a very large data set, which might suggest a general property, but there is no, let's say, theory or model that supports this.
It's just an observation, and I can say that it was a specific region of the world that I cannot disclose for commercial reason.
Okay.
Thank you.
Next, Marcella Cornia, combining vision and language from saliency to captioning.
Good morning, I'm Marcella Cornia, and my supervisor is Professor Rita Cucchiara. The title of my presentation is Combining Vision and Language from Saliency to Captioning. During the first year, I focused on saliency prediction, which is an important computer vision task that aims to identify which regions of images and videos attract the human gazes at the first glance. And in this context, we proposed a new saliency attentive model that automatically predicts a saliency map for a given input image. In particular, the core component of our model is an attentive convolutional STM that iteratively refines saliency predictions. Here are some qualitative and quantitative results. Our model was able to overcome state-of-the-art results on several saliency prediction datasets, and also was able to win an important saliency prediction challenge at CVPR, which is the most important computer vision conference. After this work, I started to explore computer vision tasks related to natural language, and in particular, I started to work on image captioning, which is the automatic generation of a textual description given an input image. Here we proposed a new captioning model that exploits the information given by our saliency prediction model on which part of the image are salient and which are contextual. In particular, our model learns different weights for salient and non-salient regions and combines them into a final attentive map to produce the final image description. We validated our solution on different captioning datasets, and we compare our model with respect to standard captioning approaches that do not leverage on the saliency information during the generation of the image description. The experimental results demonstrated the effectiveness of including the saliency information in a captioning model. Currently, I'm working on the possibility of applying captioning to complex scenarios where a higher degree of controllability is needed. And in this context, we are working on the first architecture capable of following a control signal given from the exterior during the generation of an image description. In particular, given a control signal in the form of a sequence or a set of image regions, our model can generate a caption through a recurrent architecture that predicts textual chunks grounded on image regions and following the constraints given by the control signal. Experimental results demonstrate that our model achieves state-of-the-art results on controllable image captioning, both in terms of quality of the captions and also diversity. Here are some qualitative results when using as control signal for the model either an ordered sequence of regions or a set of regions that the model is able to sort to predict the final image description. As a complementary research topic, we also explored the application of vision and language tasks and other computer vision techniques on the cultural heritage domain. And in particular, we proposed a new solution for aligning textual commentaries and illustrations from illuminated manuscript. Also, we presented a visual semantic model for cross-model retrieval for paintings and corresponding textual descriptions. Finally, I'm currently working on face retrieval, and in particular on the retrieval of faces from a set of paintings, giving a real photo of a person as input to the model. Here are some preliminary results. I want to conclude by showing the list of my publications, divided in journals, a book chapter, and also conference papers. Thank you very much for the attention.
Thank you, Marcella. Questions? I have a question.
Okay.
Can you train your data set? You know that there are ontologies and already devising salient. So, are you using some background knowledge to train your method?
No, for the moment, we are using a captioning dataset that basically, for each image, have a textual description annotated from 5 different human annotators, and we do not use ontologies or other stuff like that.
I suggest to use more semantics. Next is Luca Gagliardelli, because for the videos some students are out, but they sent us the video, their presentation. At the end of the session, we will show this presentation.
Okay. It works. Okay. So, good morning. I'm Luca Gagliardelli, and today I'll present Sparker. That is a tool to perform the entity resolution using Apache Spark. So, first of all, entity resolution has many names, but basically is the task of identifying records that pertain to the same object. So, as is shown in this example. The naive solution to perform this task consists to compare all possible pairs of records. But of course, in real cases, this is not possible due to the complexity of the problem. So, advanced techniques such as blocking and meta-blocking are needed to reduce the number of comparisons. And also, distributed frameworks such as Spark are usually used to manage all this data. So in Sparker, we mainly focused on the first 2 steps of this pipeline, and we implemented a distributed blocking and meta-blocking method. So the idea of the blocking is to extract the blocking key from the records and then compare only the records that share at least one blocking key. But there is still a problem, because usually some blocking keys are very frequent, so we still have too many comparisons. So in literature was introduced the meta-blocking that have the goal to reduce more this number of comparisons, discarding the less useful comparisons. I mean, the comparisons that are not that are superfluous. So also, several parallel implementations of meta-blocking are available, but all of them uses the repartition join that suffer of the problem that the blocks are repeated multiple times in the workers. So this produces a lot of data, making the task really slow, and also use a lot of memory to execute it, because as you can see in this example, for example, in the worker tree, these blocks are repeated multiple times. So in Sparker, we proposed a novel parallelization strategy that is similar to a broadcast join, because we generate a blocking index that then is sent to each worker. And then the worker uses the index to perform all the process. So with this index, a block is repeated only once in each worker, solving the previous problem and making the process faster and also using less resources, as is shown in these experimental results. Here we can see in the first chart on the top that our implementation is able to work on a single node on the Freebase dataset, while the other implementation, so the state-of-the-art one, needs at least 7 nodes to run, since it generates a lot of data during the execution. And moreover, on 1 node, our implementation is faster than the other one on 7 nodes. Also, in the second chart, it is possible to see the execution time on 10 nodes, and our implementation on all the data set used always outperform the other one. So in conclusion, in Sparker we implemented a novel parallelization strategy that outperformed the state-of-the-art one in terms of execution time and resource consumption. And also, as future work, I'm planning to extend the framework by adding the other steps of the entity resolution. Because now they are present, but just a preliminary level. So here there are some references about this work, and I concluded. Thank you for your attention.
Also by the people in the room. So.
Luca, what about the kind of data sources involved in the process? Are structured, semi-structured?
Okay. The data sources are semi-structured because they are JSONs, RDF, so they don't have a fixed structure. And also, okay, I don't show yet that. But usually in the blocking phase, the structure of the data is not considered because it's schema agnostic. So it's not important the type of the source.
Next candidate, Fabio Giovanardi.
Okay, good morning everyone. My name is Fabio Giovanardi and today I will follow my presentation. It's biosensing with hollow core in BT coupling fiber. So we use this kind of fiber for detecting molecular with label-free detection. So label-free detection is a particular technique. Okay, doesn't matter. Okay, it's the same. So with the label-free technique, we don't modify our molecular interest, so we don't use any label, for example, fluorescence, and it should be simpler and quicker, and eliminates problem due to the secondary detection. So in our work, we use silica, it is the material of the fiber, and we want to detect the target. And in order to reach this, we choose a probe, and if in the solution is present the target, we create an increase of silica surface. On the contrary, if there is no matching between them, we can't create any layer. So we can use this type of sensor in biomedical sector to detect fibrocystic, virus, or other kind of diseases related to DNA, or in bio application against food fraud, or in the food industry in the quality control. So we can use a different kind of fiber, for example, step index fiber, but they have different problems related to the weak interaction between the layer and the light that flows in the core. And we need another component, such as Bragg ratings, in order to convert the phase into the intensity, because the layer interacts only with the phase of the mode. So we present our work with tubular lattice fiber that the layer is here. There is a strong interaction with the target and no additional components are required. So how can we use them to detect a layer? The theory says that the transmission band is related to the thickness of each tubes. So if we increase, as I explained before, the thickness, the spectrum is shift directly proportional to the layer thickness. So for the proof of concept, we have chosen the biotin and the streptavidin molecule, the biotin for the probe and the streptavidin for a target. And this is a picture that shows two biotin molecule and one streptavidin molecule. The streptavidin is more or less 10 times greater than biotin. And this is a well-known bounding in the literature. Everybody uses for this purpose. The chemical process is the following. First of all, we clean the fiber. After, we deposit an aptase in order to bond the probe, the biotin. After that, we dry the fiber, and now it's ready to detection. And finally, we deposit on it the streptavidin, our target. So this is the schematic of optical setup. We use a supercontinued to have a greater spectrum, broadband, and OSA to measure the spectrum, and B-split array camera to monitor the output beam. These are true fiber drawn by Glophotonics, a company in France. And in particular, they work on different regions, and we choose 800 nanometers for the first one and 2,200 nanometers for the second one. The results are the following. So first of all, we measure the biotin with fiber 1 and fiber 2. The shape are well defined, so the measure is repeatable. And we measure after our target, the streptavidin. And if we zoom, we will see clearly the shift, the red shift, so the target is present. And we have done the same with the fiber 2, with the same result. I conclude stating that hollow core tube lattice fiber are a good platform for protein detector. Inhibited coupling ligand mechanism is effective in detecting proteins, and this experimental result demonstrates the feasibility. But we need more measurement in order to prove the reliability and repeatability of the system, and we change the solution. And to simplify, of course, the chemical process, because it's a bit complicated. And finally, we have to move from this proof of concept with the streptavidin to our aim, the DNA target. This is the list of journal and conference that I have done. Thank you.
Okay, I have actually several questions, but I will just pick up one. Starting from a very simple piece of information, what is the diameter of your fiber?
Yeah, just yeah.
Yeah, okay. Yeah. Okay, it's 260, sorry, go back to
more or less, sorry. Yeah. 40 more or less micrometers.
Okay, so the active area is about 40 micrometer.
Yeah.
Okay. So, and basically you're trying to use this for kind of single molecule detection. No, you have many more than one molecule in
each
the
molecule, for me, is around each tube in the inner part and the outer part. So the sensitivity is greater due to the interface between silica and the air.
Okay, so basically, maybe you did not consider the possibility to scale up this system to many parallel fibers and cover a larger area and maybe detect different molecules around your sample.
Yeah, of course. Yeah, we try with
No, I understand. I understand this is preliminary, so it's actually...
It's the first time that in the literature this type of fiber is used in order to detect a layer in biological field.
Yeah, but what I guess, what I ask, and my question is, what would be the advantage with respect to just functionalizing, for instance, a microelectrode or a nanoelectrode and use purely electrical systems? Have you considered the comparison between a purely electrical and purely optical approach as you want?
Yeah, I consider keeping the same platform. So we change, for example, the fiber, not the principle. So we have compare. I skip the result, the previous result, but we compare this type of fiber that is guiding with a particular technique that's called inhibited coupling with other type of fiber, for example, different PCF that have less sensitivity. Okay. And so, for me, I don't care the type of platform. For example, many people use to detect biological layer, nano, I don't remember the meaning, nano plasmon, but so it is a challenge. So we use fiber, they use
okay, that is clear, and you can compare. I mean, I think it's very interesting that you have a label-free approach with optical means.
Yeah, it is very simple. The idea is very simple, but the task is very difficult.
But then you may want to also to compare with the electrical.
Yeah. Okay. Thank you.
Thank you, Fabio. You have some more experiments, so I have to sign some more mission for you because
yeah.
So
every experiment result I've done in Parma. So
yes, but this the instrument that you are using becomes available. You know that they are available some hours before, so he is running to me because I have to sign the mission. Thank you.
Thank you.
So the first student is Andrea Palazzi, semi-parametric object synthesis. Dear student, yes, I look at the site and I see that you don't have your photo on the site, so I will send an email to you to collect your photo to be added to the site, okay?
No? Is there some switch or something? Cool. Okay, so cool. Okay, so hi everybody. My name is Andrea Palazzi. My supervisor is Prof. Rita Cucchiara. And in these few minutes, I'll give you a short overview of my current research topic, that is semi-parametric object synthesis. And well, let's dive in. So if the keyboard helps me. Okay, so well, let's start with the goal. So our goal is to predict the appearance of an object from a different viewpoint than the one that we are currently seeing. So in this case, for example, you see there is this car, and we may ask to ourselves how the car looks like on the other side. And clearly, it's an ill-posed problem because we don't have that information, right? But still, humans are able to perform this kind of transformation, to give a polite guess, to predict how an object looks like from a different viewpoint. And indeed, we can perform both mental rotation, so just rotating an object in our mind, and in general, mental transformation, so getting closer or farther to the object, and so on and so forth. So it's definitely an interesting problem, and we humans are quite good in doing it, so it's a nice to have feature for an intelligent system. And the current state of the art tackle this problem as a pure learning problem, so the setting is purely learning-based, purely parametric. And clearly now the deep learning is a thing, right? So the state of the art uses deep learning methods. And there are very interesting results, but there are very big limitations still, because every time you encode the visual appearance of the object in the network weights, in a compressed feature vector, you lose a lot of high-level information, so you lose object textures, so to long story short. And also both viewpoints are needed at training time, so you are doomed to train on synthetic data, and you will encounter a lot of generalization issues when it comes to real-world data. And more broadly, all these models have no explicit model of 3D transformation built in. So in a certain sense, the model every time is reinventing the wheel every image that it synthesizes. So our intuition was quite simple. That is, many man-made objects are piecewise planar, and this looks very trivial, but it's actually a good thing, because in computer vision there is a well-known transformation that is called planar homography that relates how planar surfaces as seen by different camera positions, that is, different viewpoints. So we developed a model that instead of generating a new image from scratch, instead it first detects the planar patches on the object that you can see in the middle, and in particular we leverage 2D key points which are characteristic key point indeed in the object to gather these approximate planar patches, and then we compute an homography transformation to the destination viewpoint to, let's say, bootstrap the visual appearance of the destination viewpoint. And then the learning kicks in, so only now that we have a polite guess, we train a fully convolutional network to complete this rough prediction using also synthetic data. So you can see these are surface normals and model parts. These come for free because they are synthetic, so we don't need to annotate anything. And we train this model for a task of basically image completion. That is way simpler than synthesizing everything from scratch. So we have some preliminary results. You can see clearly the images, and these are the inferred models from the network. And these are, let's say, a newer research topic I'm working on. So we are doing in these days larger scale experiments, and this work is to be submitted to ICCV, which is a computer vision conference in 1 month from now. So, well, I guess that's it.
Andrea, if I understand well, if you don't inject knowledge in your recursive networks, things are going bad, because you are injecting knowledge, the models, and
yeah, I mean,
it's a key issue for your method.
So the model indeed is called semi-parametric for this reason. I mean, the non-parametric part is the fact that we already have some prior knowledge, and why to throw it away? So we just inject it to the model. Yeah, because sometimes, I mean, it's clearly category specific, so we must be able to extract these planar patches. So it depends on the category of the object. But in many cases, we know which object we are interested in.
Just a comment. when you started your presentation, you didn't say a very important thing, that your object need to be symmetric. So
yeah, sure.
you didn't say this,
Yeah,
because
this
you are rotating something, but you think that on the other side is the same.
Yeah.
Otherwise, you cannot
Sure.
do this.
I mean,
Just a comment.
yeah, of course, it's common to all the state of the art, because at a certain point you have, sometimes they are called naturalness constraints or something like that, and this applies almost to everything that you don't see, but you expect it to be like, yeah, smooth in some way.
Thank you. So now we can show the presentation of the students that are outside, who are Giovanni Abruzzese, Lucio Fanton, and Dario Stabili. And then, you know, you have to, I don't see all the 8 posters to be shown there. They have to be put there. And we will move in 20 minutes, but the students of that have to show their poster will have also to register a small talk of 3 minutes. So prepare yourself to be effective in 3 minutes, because we will record also the presentation of the students, and everything will be available on our sites afterwards. So you can go with the last.
Good morning, I am Giovanni Abruzzese, and I'm here to present the research work performed during my second year of the PhD course in Information and Communication Technologies. My research efforts are focused on the application of machine learning for cybersecurity-related tasks. Nowadays, the popularity of machine learning is skyrocketing, and many large organizations have started to adopt these algorithms also for defending their information systems. This caused an increased demand of commercial cybersecurity products that leverage these advanced techniques. However, despite their promising achievements, the application of machine learning in the cybersecurity domain is affected by multiple issues, such as an unacceptable rate of false positives or the difficulty of acquiring and maintaining comprehensive datasets to periodically retraining the model. In this last year, I focused my attention on a problem that affects all applications of machine learning, and is of particular interest to cybersecurity: adversarial attacks. These malicious actions aim to subvert a machine learning algorithm through the creation of specific samples that are wrongly recognized by the model. The problem is that even small modifications can have a high impact on the prediction results. Comprehensive analysis on this issue from a cybersecurity perspective are scarce. Hence, we perform an extensive experimental evaluation in which we measure the performance of a botnet detector when provided with such malicious inputs. The results show that the detection rate of a similar detector dropped from 95% to lower than 1% just by adding some random bytes and increasing the duration of the network communication performed by the bots, therefore confirming the high damage potential of these attacks. This problem is further aggravated by the issues that affect existing solutions. Adversarial learning requirements would further increase the cost of acquiring and maintaining a dataset enriched with realistic adversarial samples, whereas instructing the model to exclude those features that may be modified by the attacker would decrease the performance of the detector in non-adversarial scenarios. In this context, we propose a novel method to harden detectors based on random forest against this menace. The main intuition is that existing detectors are trained with class labels, which present too rigid classification criteria for the fuzzy cyber domain. Hence, we aim to introduce some flexibility by employing probability labels. These probability labels are generated using the class labels as initial input through a process called distillation, and are then used to train the final detector. We validated this idea with thorough experiments in which we compared the detection rate of a distilled botnet detector trained with probability labels against a detector trained with regular class labels. Our solution outperforms the baseline for all the considered botnet families. However, this is just a first step, as the detection rate needs to be higher to be truly effective in real production environments. So, to conclude, machine learning is being adopted in an increasing number of domains. With regard to cybersecurity, it must be mentioned that these algorithms are still affected by many critical issues. Among these are adversarial attacks, for which existing solutions are either unfeasible or still at a very early stage. The takeaway is that these algorithms must be treated with a proper diligence, as overestimating their capabilities can lead to huge damages to modern enterprises. And with this, I'm done. These are the papers that have been published or submitted for publication and that concern all the topics discussed in this presentation. I thank you for your attention. Good morning, I am Giovanni Abruzzese.
February 22nd, D-Day presentation. Creation of a multimedia interactive didactic observatory on the zona Mead of Sulcis. This article describes the design and creation of immersive installations where users can move and explore the typical lagoon environments of southwest Sardinia. The observatory was built on behalf of Provincia di Carbonio Iglesias with the aim of making known the complexity of the lagoon environments and the fragile equilibrium that characterizes them. In addition to the cultural heritage aspect, the project was a user-centric development experiment, where different design methods were used, such as scenarios, role-playing games, storyboards and prototyping. The approach we used can be replicated as a starting point for similar projects in territorial museums, archaeological sites and reproductions of large structures. Digital cultural heritage, DCH, describes tangible and intangible cultural entities that have been created or transformed into a digital multimedia format. Today is an interdisciplinary area of knowledge that involves the research, study and analysis of digital representations of heritage and how the conservation and dissemination of culture are created and used. A technology implemented in the museum was theorized in 1947 by the Hungarian scientist D. Gabor as a method to increase the resolution of electron microscopes. It has evolved through different types of commercial applications, one of which is the holographic screen. In this project we used a device of our own creation called Hand Tracker, which uses optical and infrared technologies to identify the touch of the screen. In practice, Hand Tracker is able to extrapolate the coordinates of the hand, without the aid of gloves or other transmission devices, with respect to the surface to which is applied, is in fact capable of transforming any surface into a touch screen, regardless of size and location. The technology used to show and interact have been capacitive, up to 100 contemporary touches, optical and infrared, hand tracker, holographic. The Contents Management Software, CMS, has been developed from the point of view of multi-project use. This means having several multimedia projects selectable by the administrators. This feature is extremely important as it allows the museum to be able to easily change the virtual path of the visitors. 4 factors have been identified that have contributed: information design, information presentation, navigation mechanism, and environment setting. The results suggest the need to reduce the cognitive load of users when they explore virtual heritage environments while simultaneously present information that adds value to their understanding. The results also suggest that the inclusion of cultural information in virtual heritage environments is essential for cultural learning. Project in progress. Use of convolutional neural network in object detection activities. Goal of this project is to determine the lifestyle of a user detected by the system in order to provide him with profiled information about his habits. Example: in the marketing sector, I recognize a hippie, so I don't propose a Rolex watch but an ethnic bag. Thousands of images were sought for system training. We have verified that more images of each type are processed in our system. Most precise is the detection operation once it is in production. All the images were processed with a resize to a same format, addition of virtual frame and labels to help the next step of training the system. So we have integrated TensorFlow for image analysis and platform training. Is an open source library for deep learning which provides useful modules to implement algorithms for different types of perceptual and language comprehension tasks. TensorFlow uses convolutional neural networks, CNN, which learn using filters and applying them to images. In practice, the algorithm takes a small square and begins to apply it on the image. Each filter allows CNN to identify certain patterns in the image. CNN searches for parts of the image where a filter matches the content of the image. Once finished the testing, we will proceed with providing the system with live inputs through a webcam. Thank you for the attention.
Hello everyone, I'm Stabilitario. I'm sorry not being there with you today, but I'm currently a visiting student at Washington University in St. Louis under the supervisor of Professor Sinopoli, working on a research project that I will explain to you later. This is a brief presentation of my last year's research output in the field of cybersecurity for automotive networks and application. So two modern vehicles are composed by both mechanical and electrical parts that cooperate to implement a different feature. Electronic components are called electronic control units, of course, that are generally tied to a particular safety relevant function. One ECU is particularly responsible for one of the many security relevant functions, but of course each ECU needs to operate not only with the values of the sensor attached to it, but it needs to know even the value of other sensors spread across the network. So they need to communicate with each other, and of course they are connected on one of the many vehicle internal networks. The most deployed network protocol in today's vehicle is the CAN bus, that is a controller area network. It's a pretty old standard. The last version of the CAN bus is dated 1991. So it's not the CAN bus is not the only network protocol for in-vehicle communication, but of course it's the most deployed. Messages on the CAN bus are sent with a particular structure, that is the data frame. The data part of the data frame, the one highlighted in red, encodes different values of the sensor readings from a particular ECU. Each message has an identifier, and the meaning of this particular field depends on the value of the identifier. But of course the data field encoding for its syntax and the semantic are confidential information and not publicly available. So if anyone wants to know the meaning of the signals encoded in the data frame, it has to reverse engineer them. This is particularly an issue because when you're thinking about cybersecurity, the attackers could have a heavily time-consuming and human-intensive manual reverse engineering process in order to know the syntax and the semantics of each signal. But cybersecurity researchers cannot. So we wanted to propose a novel algorithm that focused on the automatic reverse engineering of automotive data frames. The proposed algorithm is called READ, and the idea, of course, was to bring an automatic signal extraction from automotive data frames as an enabler for future research, and we used a bit flip rate evaluated on the single bits composing the data field. So you can see the structure of the algorithm here on the right. After we gathered enough payloads to have data to work with, the algorithm enters in the pre-processing phase when it inspected every bit and generates for every bit a bit flip rate corresponding to that particular bit. And then with the bit flip rate, we evaluate the magnitude array. In the first phase of the algorithm, we evaluate the preliminary boundaries from the magnitude array, while in the second phase, we use the preliminary references and the bit flip rate to extract enhanced references and to label them according to what we think it is that particular signal. In literature, there was only one other algorithm that proposed an automatic field extraction method, and in the paper, in the last year output, we implemented the other algorithm and tested our proposal with a particular the particular type of data that we have, and of course we have the specification. So here in the plot, you can see on the top row we have the output of our algorithm. The bottom one is the output of the other algorithm, and the red vertical line represents the specification and the exact boundary of the signal represented, of the data frame represented. And as you can see, in this particular case, we were able to 100% extract the correct boundaries while the other algorithm struggles. So as I already told you, I'm currently in St. Louis working with Professor Bruno Silopoli for a research project. The idea and the basic of this research project is to inspect the vehicle system not only from of the protocols and of the messages that are sent on the vehicle network, but to bring it to have a more advanced representation as the vehicle as a cyber-physical system. More in particular, we are focusing on the powertrain part of the vehicle. And the idea is, of course, to create a simulation model that we can use for both cyber-physical approaches, cybersecurity physical approaches, and for cybersecurity classical approaches. But we're still in the early phases, and I don't have any early results to explain to you. Well, thank you for your time, and I hope to see you all back in August. Bye-bye.
So the second, Lucio Fanton, wrote the text on Google, and so the presentation, the speech is by Google, you know. It's not his voice. But if you want to train yourself for the good English, you can do the same for the presentation. So now we have the poster, and I invite the member of the council to look at the poster of the students, and then the students will register their speech of 1 minute. The students which are involved in this activity are Bergamini Luca, Bombarda Davide, Fabri Matteo, Grazioli Filippo, Morrone Giovanni, Paganelli Matteo, Parmigiani Nicolò, Salierno Giulio, Zani Nicolò. I invite the student to, to look at the poster of the other student. We will have a look and go, and we have to start our council meeting our council meeting because we have to deliver for the admission of the students for the final examination. So we will stay just a few minutes here. Thank you so much.
So hello everybody, I'm Luca Bergamini and I'm here to talk to you about the work I've done in the last year on multi-view embedding for cathode identification. This research started as a collaboration between the Image Lab from the University of Modena and Reggio Emilia and the Italian startup for trade. So the goal is quite ambitious, in fact, and it is to being able to re-identify cows using just a single or few pictures. So only images in the wild with no tight constraints. Of course, we didn't have, when we started, a large data set to train our methods on. So we gathered and we collect like 1,000 of pictures from 100 of different subjects from different regions of Italy. And well, the motivation for doing this is that the number of cows is really humongous. There have been like more than 100 billions of cows in the world, and this animal may transmit pathogens. So we developed a method leveraging a multi-view CNN, which combine two views of the cow, a profile, a side view, and a frontal view. This network compresses information in a short embedding, and we can then compare this embedding to find if we already have seen this cow in our dataset. These are the results. They show that our method clearly outperforms both shallow method and deep method trained for, so developed for the humans and not for cows. So thanks everybody. If you want to know more, please ask me.
Good morning, I'm Matteo Paganelli and my tutor is Francesco Guerra. My current research activity is about data explanation, and in particular we have developed a new approach that generates a description, an explanation of a dataset through the use of description. Here we have some example of description. They are a set of compact, readable formulas of Boolean predicates. And this approach is organized in 3 different steps. In the first step, the dataset is partitioned in a series of related information. Then, in the second step, for each partition, are generated a series of descriptions that are called the formulas. And in the final phase, we combine the formulas in order to obtain a description for the entire dataset. The main issue of addressed in this process is to identifying the best description according to different user needs. So we have defined 3 different parameters that are coverage, degree, and diversity. And we use these parameters to qualify description and understand which description are more relevant for the user. So we score the different description with these different parameters, and we use an optimization algorithm such as the Viterbi algorithm to identifying the best combination, the optimal combination of the formulas, and thus obtaining a description for the entire dataset. With a series of experimental evaluation in terms of efficiency, effectiveness, both in quantitative and qualitative way, we have demonstrated that our approach is a viable tool for providing an insight, an intuition of a dataset. Thank you.
Good morning, I'm Giovanni Morrone, and my tutor is Professor Sonia Bergamaschi. I present my work on audiovisual speech enhancement in a cocktail party scenario. This work is made in collaboration with the Istituto Italiano di Tecnologia. The Cochrane party problem is the task of amplify one voice among many sensors. This ability is called the Cochrane party effect. In a computational terms, this task is called speech enhancement. In speech enhancement model, we have a noise spectrogram that is a time frequency representation of a speech signal, and we want to estimate a time frequency mask that is element was multiplied by the noise spectrum to obtain the enhanced spectrum. Since there are many voices in a speech signal, we need an attention signal that provide an additional information about the speaker of interest. We use the facial movements of the speaker of interest as as additional information. We use a Petrine phase random extractor that give us a salient point about mouth noise and other points of the face. Now we want to estimate different type of masks. A target panel mask that is acoustic context independent, and a data binary mask. We experiment with the file models that combines the noise spectrum and the visual feature in different ways. Our results are very promising on two relatively small datasets such as GRID and TCD TIMIT. The best model is the audiovisual concat refinement model that is a model with two-stage enhancement with two different masks. In conclusion, we obtain a speaker-independent speech enhancement model, and most importantly, we, thanks to the use of Petrine, the phase random extractor, we have not to use UG datasets for this task. Thank you.
My name is Nicolaus Zani. I'm a PhD student at the ICT Doctorate School. The topic of my research is variability-aware technology design co-optimization, a revised Pelgrim's Law approach. So the purpose of this work is to investigate the influence of variability in the design of modern nanoelectronic circuits. The problem with the production of devices today is that every time you fabricate a wafer, you will have different devices with nominally identical performances, but then we'll have a distribution of their parameters that are due to mismatches between components and the process itself. So every time a circuit is designed, then the design itself must account for these variations. But the approach that is currently adopted by designers is based on fixed corner models that in some way overestimate or underestimate the variations. So the idea behind our work is to perform more physical sound simulations in order to improve the design approach that is currently available for accounting for variations. So based on current Intel's modern technology, FinFET technology, we assess the impact of local and global variations on single devices to extract what is the variation for a single device, but in general terms for the whole circuit design. In terms of this Pilgrim law, that is the model that is currently used by circuit designers. So we can see that there is a deviation from this law, and the TCAD simulations, that are the physics-based simulations, will actually give you the correct prediction, but the model used by the designers will not. So it's important that for very small devices to change this rule with this more accurate results, to sort of having a revised model, simple model, to still be able to accurately and fastly design circuits correctly, but to also have more accurate results for very scale dimensions. Thank you.
I am Davide Bombarda. I present my research activity on COC usage in railway signaling application. The context of railway signaling is facing a revolution, introducing the new technologies on this field that is traditionally much traditional, conventional technology uses. The keywords in the railway field is safety first, then innovation, reliability, and robustness. So my activity research my recent activity research regards track secret contactless signal analyzer. That is a signal analyzer that analyzes the signals that run in a track circuit. A track circuit is a circuit that detects the presence of a train on a section of track. So in this section of track, we send a signal pattern and some modulation signals. We want to detect the presence of the signal and its correspondence to the specifications of the constructor. More, we want to detect the presence of incoming faults in the system, since the system is robust but unopposed to environmental conditions. And so we need machine learning to detect anomalies in the signal, the measured, and so we can say to the maintainer to intervene in the given field. So since now, from November, we have designed a compensation filter for the magnetic antenna that is used to detect the signals while the track is using in normal operation. And now I am elaborating the software that is analyzing the signal.
My name is Giulio Salierno, and my PhD doctorate is funded by Alstom, and in this work we bring formal methods into an existing design developments of railway system software based. In particular, we introduce the state chart models to model the existing system and to replace the relay logic design. And in particular, we augment these state chart models with the nested variables to represent the device composing the system. Then we translate this model into a formal specification using a temporal logic for action language. And in particular, we verify this formal specification using a model checking approach. And in particular, we verify two kinds of properties. The first one is safety properties to verify that something bad won't happen. And we express these properties as invariants. And the second one is the Leibniz properties that are expressed as temporal formulas. In particular, in Leibniz properties, we verify that something good will eventually happen. Finally, we designed a graph-based algorithm to extract executable code from this model, and this kind of code can be executed on in a virtual environment for simulation, and in particular, it allows to specify a specification without involving in an implementation.